Okay, yeah, thanks for the invitation to speak. I am going to tell you some work that I've been doing with my collaborators. This turned into a very big paper, but I'm going to talk about just some small parts of it. This is work mainly led by Marcus Kessering, so I hope I can do it justice. Okay, so normally I would put a fancy picture on the front of my slides, and right now I've just got this little noughts and crosses table. I'm going to try and argue to you that this is the right way to think about the color code, and thinking about the color code in this way helps us make new Floquet codes. So maybe remembering what Zhenghan was talking about, what I have is some constructions for Floquet codes. It's a little more general maybe than the honeycomb code. Maybe it can be generalized further, I don't know, but maybe it's an example that might help with the theory. Okay, so what I want to talk about to begin, I'm going to talk about Anyon models, and I really want to talk about the vacuum particle. That's quite interesting for it's normally the boring one, but that's quite interesting for studying Anyon condensation. Then I'm going to spend some time introducing the color code, and I'm going to try and tell you why we should be thinking about the color code in terms of a boson table. After that, I'm going to talk about how we use this boson table to understand Anyon condensation in the color code. And it's quite an interesting example of condensation because we recover a non-trivial phase. When we condense a boson in the color code, we get a toric code phase. And what's more, we actually get a Floquet code. And I'm going to try and reproduce the honeycomb code and some other codes, Floquet codes using condensation. I'm going to introduce a new kind of Floquet code that, as well as not having logical operators, if you regard it as a subsystem code, it also doesn't have stabilizers. So I think this is an interesting example. Okay, so that's the outline of my talk. We already heard a bit about anyons, so I'll try and be a bit fast at the beginning. Okay, so we're interested in topological quantum error correcting codes, and these are built on Anyon models. And Anyon models have a bunch of properties that are quite important to describe the model. So for example, in the case of the toric code, which we've heard about in the last two talks, we have a bunch of, well, we have a list of charges. So for example, in the toric code model, we have an E charge, which is an electric particle, and an M charge, which is a magnetic particle. And these names came from Kitaya's original work where he introduced this model due to an Aharonov-Bohm effect that you can see in the toric code phase. Okay, so to describe these labels, they also have some other data associated to them. They have exchange statistics, which is where you swap two of them. You can ask, what is this? And in this case, they're either bosons or they're fermions. We have fusion rules, which is what happens when you bring two anyons close together. What anyon do you get out of that? And one example in the case of the toric code is we get a fermionic charge if we combine an E and an M. So this is a symbol for fusion. And what's really interesting about anyons in 2 dimensions, more so than in 3 dimensions, is that if we braid anyons around one another, we get non-trivial braid statistics. So we can ask what happens if we braid one type of anyon around another type of anyon. And in general, we can get some non-trivial phases. Sometimes we do, sometimes we don't. In the color code, things get a bit more exotic, so I'm going to spend some time introducing that. Okay, and roughly the way you can think about topological quantum error correcting codes working is we make some lattice of qubits, and we produce some phase of matter, and we have logical operators that act on our encoded ground space, and those physically, you can think of these logical operators as being hopping operators that drag anyons around non-trivial cycles on these manifolds. So for example, we might think of this loop as dragging some anyon charge around a torus, and if we act this operator on our topological code, it will transform the ground state in some non-trivial way. Okay, so I want to talk about nothing. I'm going to hold a quiz at the end, and if you tell me what you got from this talk is nothing, then that's what I want, okay? Now, yeah, so I'm going to talk a bit about the vacuum. The vacuum Normally people don't care about the vacuum. When people introduce their anion labels, they say, this is the vacuum charge, it means there's no particle there, so just forget about it. I don't want to forget about it. I want to talk about what the vacuum does. It's one of the charges in the set of charges, and we normally label it with a 1. So what properties does the vacuum particle, which is no particle, have? Okay, so we have these R symbols. So these R symbols tell you the phase you get when you exchange 2 particles. And if we exchange 2 nothing particles, nothing happens. Okay. We also have fusion rules. Fusion rules say if you have a charge and you fuse it with a vacuum particle, which is nothing, what comes out on the other side is the same thing, because we just combined something with nothing and we got the same thing back. And likewise, if we take a particle like an anion and we braid it with nothing, then nothing changes. It's still just the same charge. So this is the vacuum, and this is kind of a weird thing to say right now, but when I get onto anion condensation, this is a bit more important. Okay, so now let me talk about the color code. The color code is the model I'm mainly going to be interested in until I get to Floquet codes. So the color code is a stabilizer code. You can think of it as having some code space, which is specified by the common +1 eigenspace of a bunch of commuting Pauli terms. And in the case of the color code, well, I'm going to think of a hexagonal lattice, and every single hexagon has a Pauli X type stabilizer with Pauli X on every single vertex of a hexagon, where there's 1 qubit on every single vertex of the hexagonal lattice. And every single hexagon also has a Pauli Z stabilizer plaquette. So it'll be Z, 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 Z around that hexagon. Yeah, so the code space should be the common +1 eigenspace of all of these stabilizer operators. And although this is about quantum error correction, it's also quite helpful to think of this as a Hamiltonian model. So if I take all of these stabilizers and write down a Hamiltonian as the negative sum of all these stabilizers, then now we have some topological field of ground space, and I can talk about violations and excitations of this Hamiltonian like they're particles, and that's going to be useful. So we can create excitations on this Hamiltonian by applying Pauli operators, and these Pauli operators create bosons or fermions, depending on what kind of operator you apply. So I have some pictures of those over here. So for example, I can apply 2 Pauli X operators on these 2 edges, and it'll create 2 excitations on these 2 plaquettes, because those 2 plaquettes don't commute with the operator I just applied. These are anyons, and these anyons need a label or a name. So these anyons live on green hexagons, so they have a green label. And because I used a Pauli X operator to make this string, I also give them an X label. And in general, this is how I'm going to label all the bosons in my color code. They have a Pauli label and a color label. So that's a green X, that's a blue X, that's a red Y, and so on and so on. Sorry, these are a little bit small. So that's how we label the excitations of the color code. We have a color depending on where the string terminates, what color the hexagon is. And we have a Pauli label depending on what Pauli string we use to create that excitation. Okay, and yeah, that's all I have to say about this slide. So what I'm going to try and argue to you is that the best way to describe the bosons of the color code, it seems quite odd at first. This is something we introduced in an older paper from 2018. So it's an overcomplete set of bosons. You can describe the full Anyon model of the color code with just 4 bosons. I want to write down all 9 of them and then throw out the fermions. And what I want to argue is the right way to do this is to organize them in this boson table, where we have Pauli labels organized in the rows. So all of the ones in this top row are X labeled, all of the ones in this middle row are Y labeled, and all the ones in this bottom row are Z labeled. And the colors, the columns are separated by colors. So I have a red column, a green column, and a blue column. This particular arrangement is quite helpful. So I should also mention Alex's work, who just talked earlier. He showed that, well, in his paper, he shows how you can write down the color code as 2 copies of the surface code. So there's this transformation that I can mention if we need to talk about that. Okay, so as I said, all of these excitations are bosons. We can move these particles around by adding string operators around some location. So what we find is if we create a pair of color code bosons, in this case this is a string of red Z terms, and we cross them, we don't introduce any phase. So the exchange on all of these terms are trivial. So in this sense, all of the particles in this table are bosons. So here I picked the red Z string, but I could have picked any Pauli label and any color label. And you can kind of tell that this is a symmetric, there's a color symmetry by exchanging the colors, and the model is the same. And it doesn't matter which Pauli you use either. You can easily check using these types of calculations that everything here is a boson. Okay, so that's quite a boring part of this table, but let me get to some other parts. Now, as I said, we also have fusion rules among the color code bosons, or any kind of fermion, anyon. And what that tells you is what happens if you bring 2 anyons close together, what happens at the end. And you can kind of calculate that from the string operators as well. So for example, because I can locally create two of these bosons, in this case green X with a single string, this means they annihilate themselves. If I bring 2 green X's together, they annihilate, and so yeah, they're all their own antiparticle. So if I take 2 of any boson from this table from the same location, they annihilate themselves. Okay, but what else is interesting about this table is the fusion is closed through the rows and through the columns. So for example, here I've shown I can create locally a blue X, a green X, and a red X. So that means, equivalently, I can say the fusion of a green X and a red X is a blue X. So the fusion is closed in this row. So what I've just shown there is the red X fused with the green X makes the blue. And I can any pair of bosons from the same row will give the 3rd boson from that row. Likewise, the columns also give you, the columns also are closed under fusion. So this string operator shows that a red Z, a red Y, and a red X can be created locally. Or what that means is a red X and a Y can be fused to make a Z. So red X fused with red Y makes a red Z. So the fusion is also closed through the columns of this table. Lastly, the other useful thing here is that you get non-trivial braid statistics between 2 bosons of the color code if and only if the 2 bosons are from 2 different rows and columns. You work this out by looking at the commutation relations between the string operators that create these different excitations, and it's easy to check that a red X and a red Z particle, their string operators commute if you try and cross them. So because they share the same column, they braid trivially with one another. Likewise, if you have a Pauli X red and a Pauli X green, they're going to braid trivially because Pauli X commutes with Pauli X. So 2 charges in the same row, they braid trivially with one another. What's important if you want 2 color code bosons to braid non-trivially with one another is they have to be in both a different row and a different column. Yeah, okay, so to summarize, this table is useful because the fusion is closed in the rows and the columns. Braiding is trivial in the rows and the columns, and it's only non-trivial with 2 bosons in opposite rows and opposite columns. And also this labels all of the bosons of the color code. I have a feeling that these are the 3x3 labels that Zheng Han mentioned in his talk. Okay, so I spent a long time talking about the vacuum, and I've not talked about that yet, but I'm going to go back now to anyon condensation. So anyon condensation is where you take a boson, and you put it in the identity. You say that the boson is identified with the vacuum. It's now part of the vacuum. So as you can tell, there are lots of symmetries in this table. As long as the rows and the columns are preserved, it doesn't matter which one I chose. So I'm going to show you what happens if I just try to condense one color code boson, and I'll pick the red X. So I'm going to write down that the red X is identified with the vacuum, and I put a big black spot in that location to say that that one's condensed. Okay, now what I want to do is I want to ask what are the consequences of this condensation on all the other bosons in the table. If you remember before, what the vacuum has to do is it braids trivially with itself. Nothing braids nothing, just fine. The vacuum braids trivially with all the other anyons in the model, and it also fuses trivially with all the other anyons in the model. So what does that mean for the remaining bosons that I didn't condense? Okay, well, I want to check that the vacuum still behaves correctly when I've got the red X boson in the vacuum as well. So firstly, because it's a boson, the exchange statistics are still trivial, and that's what I need. That's easy to check. I just jumped a slide. Okay, now this does have an effect on some of the other bosons in the model. I need all of my bosons to, or all of my anyons to braid trivially with the vacuum. But because of the properties of this boson table, not all of them were doing that, right? Anything that doesn't share a row or a column with the condensed charge, that's not allowed to be an anyon anymore because it doesn't braid trivially with my new vacuum that now contains the red X. So what I say is these charges with a cross, they're confined. Confined means they're not in the same row or the same column as the condensed charge. Okay, but the way the color code works is there are still some charges that braid trivially with the red X boson that I condensed. So these are still what we would call deconfined charges. So I do still have some non-trivial topological order. And yeah, let me just talk about that. So I finally want to talk about the fusion, really. So in this case, all I've said in this slide is if I condense the red X, the red Y and red Z braid trivially with the red X, so they're good. And the green X and the blue X braid trivially with red X, so they're still deconfined charges. So I still have some kind of an anyon model. The last thing I'm going to do is I'm going to tell you that that's a toric code model, but I just have to talk about the fusion a little bit more to do that. Okay, so as I said, when we fuse with the vacuum, we're supposed to get the same anyon out. We fuse anyon A, any anyon. With the vacuum, we get anyon A. Nothing changed. So now what happens when the red X charge is also in the vacuum? Well, now what we need is for A fused with red X to give A back. However, in the color code model, in the original parent model, we had blue X fused with red X gave green X. Now these are still my deconfined charges, and that's not quite what I want. What I want is for the red X charge, which is in my vacuum, is condensed, fused with the blue X to give the blue X back. So the last thing to say is that because I've condensed the red X charge, for all of this to be consistent, I need that the green X is unified with the blue X. And this is just a consequence of identifying the red X charge with the vacuum. So by a similar argument, I can also say that the red Y charge and the red Z charge, they're also unified by condensing the red X charge. Okay, so this is now how I'm going to draw a picture of condensation in the color code using this boson table. I started with my parent model, which had all of the 9 color code bosons. I decided to condense the red X boson. That confined all of the charges that are not in the same row or the same column as the red X. But I did get some deconfined charges that are now unified. The red Y and the red Z are now this orange particle, and the green X and the blue X are now this blue particle that live here and here. And these are now the same particle for the argument I made before. What's more, these charges, these bosons, braid non-trivially with these bosons. So I now have 2 bosons that braid non-trivially with one another. So this is a model we're all familiar with, and that's the toric code. I told you that before I started doing this. I wasn't going to check to see if anyone knew the answer. Okay, so what I did, I condensed a red X, and I got a toric code out from the color code. Okay, so how do I do that physically? How do I do that physically? Well, I start with a color code, and I measure all of the red X edges. I start with a color code model, and I measure two-body XX terms on all of the red edges. So when I say a red edge, I say an edge is red if it's the two qubits on an edge that connects two red hexagons. So that's a red edge because it connects this red and this red hexagon. So that measurement condenses all of the red X bosons of the color code and gives me a toric code phase. You can also think about this in the Hamiltonian picture. If I started with a color code Hamiltonian H0 and I added some hopping terms to the Hamiltonian, the hopping terms for red X bosons, then I would also condense the red X charges and recover the toric code phase. So I added, so this was actually in response to Fiona's question, if she's still there, maybe no, but she asked before, what does it mean? If you have a symmetry that's not isomorphic, that's more or less what we have. You can imagine the color code in space-time that's then condensed, where we condense one charge, and then after that time, we have a toric code phase. Okay, and so this is also, Zhenghan was also saying this with the superlattice. So over here I've drawn the color code where I've measured these red X terms, and that anti-commuted with the Z stabilizers on the red hexagon. So I've left just an X here to show that there's only an X stabilizer left. But these X measurements commuted with the blue and the green hexagon, so I still have an X and a Z stabilizer on all the blue and all the green hexagons. So to the left, to show you it's really a toric code, I've drawn the toric code in kind of the more conventional way, as Kitaev would, with qubits on the edges. The black spots are qubits, and the X stabilizers are now star operators. You can see a star on top of this red X hexagon. These two-body terms are small stars with just two legs. And because the blue and the green terms still have their Z stabilizers, they're Floquets. So this is a different way of drawing the superlattice that Zhenghan showed us. Okay. So, okay, let me just say one more thing about condensation, then I'll talk about Floquet codes. So one example of condensation that we know very well is boundaries of topological codes. We can condense, at the boundary, we can regard three different charges as having been condensed. So at this boundary, we have condensed all the blue charges. This is a standard color code boundary. We'll call it a blue boundary because we can locally create blue charges from this boundary. Okay. A way you can create this boundary is you condense all of the blue charges just on the outside of this boundary. So now we can't make any red or green charges, and we can locally create blue charges at this location. So back in the boson table picture, this corresponds to condensing a whole column, the blue column of the boson table. Likewise, we can create, in the same way we can condense a column, we can also condense a row, and this gives us what we call a Pauli boundary, where we can make any color as long as the Pauli label is a Z. So this is an example of condensation that everybody should be familiar with. So we wrote about this in this older paper. And so these are actually Lagrangian subgroups of the bosons of the Anyon model, which is a complete subset of bosons that all braid trivially together. And because of the way I set up the boson table, the rows and the columns specifically respect these Lagrangian subgroups and give us all the different types of boundaries that are allowed with the color code. Okay, so just to advertise a little bit, these ideas of Anyon condensation with the color code, we've looked at lots of different code deformations and gates and computational operations we can make using condensation by condensing different anyons of the color code, and how to do computational operations. And so lots of the other results in this was becoming quite a big paper. We describe a lot of different kinds of computations using anyon condensation. So that's also an answer to Fiona's question from before, if she's still listening. Okay, but I want to talk about Floquet codes. I'm now up to Floquet codes. And what we saw in the last talk is that one instance of the honeycomb code is more or less exactly, up to a local basis change, a condensed color code. This is exactly one instantaneous stabilizer group of the honeycomb code. And what I want to argue is that actually all we have to do these transformations is recondense one of the confined charges of the color code. And what's quite nice about this is, in fact, by looking not just at the honeycomb code or the Floquet code as a piece in the toric code phase, if we look at it at this parent phase, where we have lots of confined charges that we're allowed to recondense, then what we recover is a Floquet code. And maybe a way you can think about this is, well, you know, we can add more symmetries to the model, where we can make a bigger parent model with lots of non-trivial phases that we can condense to move through different phases. So let me show you one Floquet code transformation. What we do is we begin with a red X condensed phase, which has an E charge on the orange spots and a M charge on the blue spots. And then we condense the green Y, for example. And now in the green Y charge, in the green Y condensed phase, we still have an E and we still have an M. But this transformation is allowed because the original phase and the new phase, they have a common deconfined charge. So because there's a deconfined charge before and after the transformation, that anyon survives and we maintain some logical information in the ground space. Okay, so this is roughly how we think about, or how I like to think about how the honeycomb code and other kinds of Floquet codes work. Okay, so we can talk about this in terms of microscopic details. So specifically, when we make this transformation, say I start at the bottom here with the red X condensed, and then I condense what was a confined charge, the green Y charge, and I map from this code onto this code. The logical operators survive because this star operator and this star operator are in common. That means this E charge becomes this E charge after the transformation. And likewise, this M charge becomes this M charge after the transformation. So this means there is some preserved logical operator when we make this transformation. At the level of the code, all kinds of things happen. So we go from this condensed color code to this one, where in this picture we have the green X edge term, sorry, the red X edge terms and red X Floquet terms. And in this model, we have the red Z terms turned back on. The green X terms are turned off. We lose the red edge terms, and we get these green Z terms as well. So yeah, what does this transformation do? Here I've summarized it. The green Pauli X stabilizers are turned on. We had them here, now we turn them off. The red Pauli Z stabilizers, they get turned back on. That's because the product of my green Z terms around the boundary of a red edge, that turns a red Z stabilizer back. And we also get to measure a blue Z stabilizer. So the ZZ terms around this plaquette, they turn, these stabilizers are now measured. I was in an eigenstate of these stabilizers, and I just measured an eigenstate of these stabilizers. So if an error occurred in the meantime, we actually detected an error. Like that should be in a known eigenstate, and if that eigenstate is flipped, then something's gone wrong. And you can also see that up to symmetries and Pauli labels and color labels, I haven't really changed the code. It's just shifted a bit, and the Pauli labels have changed. Okay, so that's how the Floquet code and the honeycomb code goes. So this is the code that Zhenghan has told us about already. This is the honeycomb code up to a local basis change. Roughly what they do is higher in Hastings, they start with a condensed red X, then they condense green Y, and then blue Z. So it's worth saying that how you label the E's and M's on this term, on this code, determines how the E's and M's are labeled on this code as well. Because this was the E here in this row, this becomes the E in the next term as well. Likewise, because this was the M, this too is the M. So as you can see, you have this EM symmetry after one whole cycle. I go red X, green Y, blue Z, red X. If you just follow the transformations, the E's become M's and the M's become E's. So you actually have to go around twice to get the E's back to E's and the M's back to M's. So that's why I've drawn it 6 times and not just 3 times. But you can pick whatever you want. Like there's lots of freedom. I start with a condensed color code. I can then choose to recondense any confined charge that I want to. And we made a new Floquet code this way. We made what we call the Floquet color code. So what did we condense? We wanted a CSS code, so we started with red X, then we went to green Z, then blue X, red Z, green X, blue Z, and then back to red X again. So we never even measure a Y check. And we call this the Floquet color code. And I'll tell you why we do that in just a moment. Okay, so how does this work? So as I say, the colors go red, blue, green, and I alternate X, Z, X, Z, X. Okay, so here's one red hexagon. I have to do error correction with this. Like, why does this have a threshold? So at some time, I measure these green X edges. That initializes a red X stabilizer. Now, everything I do between this time and the last time commutes with this plaquette that I just created. This two-body ZZ term, they share 2 sites, so they commute with the plaquette. These are X terms, so they commute with the plaquette. These ZZ terms, they share 2 sites with every X hexagon. And then finally, I double-check the hexagon. I measure blue X edges around the red hexagon again. So to detect errors between this time and this time, I compared the outcome of this stabilizer measurement to this one. I've drawn the same picture, the same steps for the honeycomb code to the left, to the right, sorry, but I'm going to hurry up. Okay, so what's really cool about this code is you don't even keep the stabilizer. The stabilizer group isn't preserved. I showed you that you create an X hexagon, and then 4 time steps later, you measure the X hexagon again. But then on the 6th time step, you actually kill it. So here's that red hexagon I just showed you. And the next time step, I measure this red Z term that doesn't commute with this stabilizer. That means this stabilizer dies. But at the next time step, I turn it back on again. This is kind of cool to me that not only, so in Hastings and Harper's paper, they're very excited that you have this dynamically driven logical operator, but here we also have dynamically driven stabilizers. If you write this down as a subsystem code, there is nothing. There is only gauge. Okay, nevertheless, we do still get to do error correction because as soon as we get done measuring this red hexagon, those same blue edges turn on a green hexagon. All the while, this blue one was switched on. Now, thing is, every single qubit sees a red, a blue, and a green hexagon. So all the time, every single qubit is always touching 2 stabilizers that are turned on. So every single error always triggers 2 stabilizers and you're good. Error correction works fine, and you can decode this with matching. So the other thing that's interesting with this code, so even though you turn your stabilizers off, every single hexagon we measure an X stabilizer and a Z stabilizer. So while we're measuring X's over here, the Z checks are also measuring these Z checks over here, and it kind of works in the same way, just a step out of phase. So this is what we call the Floquet color code. I think the next slide is I used STIM, the Google Craig Gidney's Clifford-Gate simulator and pi matching, and I found a threshold for this code. It's about 0.3%, which is very competitive with the simulations that Google did, Gidney, Newman, and McEwen. When I say competitive, I think they're a little bit better, but it's kind of hard to tell because they're a bit fuzzy with the numbers in that paper. I'm a bit fuzzy too. Okay, so one other thing that's what I think is really good about Anyon condensation is you can also construct boundaries for these kinds of codes. So what we need if we want to make a planar version of this code is a rough boundary and a smooth boundary. So what we can do, if we want a constructive way of making these boundaries, we can actually appeal to the parent theory to design the boundaries, and the boundaries as we undergo transformations. So here we have on this side, well, I'm going to explain this picture in the next couple of slides, and then I should be just about done. Sorry, I'm overrunning the half hour I'm supposed to speak for. Okay. So it's worth saying, like, Hare and Hastings have already come up with these boundaries, and maybe the Dennis paper is a good one to learn about what rough and smooth boundaries are. But roughly speaking, a rough boundary is supposed to absorb an E charge, and a smooth boundary is supposed to absorb an M charge. We learned about those in the earlier talk. Okay, so here's how you do it. Here's how you make boundaries in a constructive way. You say, I'm going from the color code, the parent model, and I'm going to condense a red X boson, and this is going to give me an E and an M. Now, I want, if this is supposed to be my rough boundary that absorbs an E, oh, actually, sorry, this is my E and this is my M. I've messed up my convention. So this is an E and this is an M. So in the parent theory, my E charges are all red. So if I began with the color code with a red boundary that absorbs all the red charges, so here's the picture of the boson table once again with all the red charges condensed. When I actually perform this condensation operation, this red boundary becomes a rough boundary in exactly the way I want. Similarly, when I condense the smooth boundary, this is going to be my M. The M's in the parent theory used to be X charges, a green X and a blue X. This should have been a Pauli X boundary. So if I began in my parent theory with all of the Pauli X condensers, a Pauli X boundary over here, when I condense the model, I get exactly a smooth boundary, just how I wanted. So that's the idea we have. And this construction seems to have worked pretty well. It also tells us how the transformations have to go. So because this, say, was my E, my red X, this was my E charge. So this was my rough boundary. When I make a transformation, I start with a red X condensed code, and I go to a green Z condensed code. Well, now the E charge I had here is now it now needs to be a Z boundary. Oh no, I screwed up. Hang on, that was the red one, and then it became a Z one. So for this boundary to work correctly, the red boundary has to transform into a Z boundary. And this has to be consistent just by watching the transformations through this boson table. And yeah, so we can calculate how the boundaries have to transform. It's much easier to work out what the boundaries are in the parent theory and then just calculate how the stabilizers are supposed to look. So yeah, here is a picture of those boundary transformations as we go through the Floquet color code. It's easy enough. I'm going to just speed up a little bit, okay? I've got like 2 more slides. To summarize, we have calculated all the microscopic details of these types of boundaries as well. So yeah, here we see how the stabilizers transform as we switch through a condensed red boundary and then a condensed Z boundary and a condensed blue boundary and a condensed Z boundary and so on and so on. I think that's how it goes. And we worked out how all these detectors work, the stabilizer cells in the space-time. And what's cool about the way we constructed these, so one thing that you notice in all of these other papers, the Google paper and also the Microsoft numerical paper that recently appeared, is the code likes to try and walk around. As you transform the code, the boundary sort of has to move, and if you only have a finite-sized chip, the code kind of wants to walk off the side of the chip. And so to get around this, all the papers seem to look at different types of transformations, so it walks in one direction and walks the other way. And they were kind of stuck about the ways they're allowed to transform their boundaries. Using what we know about the color codes, we actually found some boundaries that don't even drift. It just stays exactly where you want it to be. They still transform in a slightly non-trivial way, but the code doesn't really move. You can just say, these qubits are allocated to this block of code, and it just sits there. So that's quite nice. We have some static Floquet codes now. So that came out of our construction by viewing the Floquet code as a condensed color code. And yeah, it's nice. It's not too difficult to make boundaries in this way. I'm running out of time, but this is my outlook slide. I find that thinking about Anyon condensation on the color code is a really good way to view the Floquet code and how the Floquet code transformations work, specifically by taking a code with a parent code with some condensed charges and confined charges and deconfined charges, and then recondensing a confined charge. We can very easily write down these Floquet code transformations. With the code we made a Floquet color code. That's what we did. I've tried to argue to you very quickly that this is how we write down the boundaries. We can write down boundaries in a constructive way. I've kind of argued that the periodicity isn't very important. You can kind of choose a random path through this, this boson table as long as you condense one of the 4 confined charges. You don't have to follow a specific pattern. That wasn't explicit, but it's kind of obvious from the things I've been telling you. And what's more, in our example, we don't even have local stabilizers. We're dynamically generating local stabilizers as well as logical operators, whereas in the honeycomb code, it's just an example where we only generate dynamical logical operators. So maybe this is a nice way to generalize Floquet codes in general. We look for some parent Anyon theory with lots of non-trivial condensates, and we work for paths through these condensates. The color code is quite nice just because we have this nice structure in the boson table. It'd be nice to maybe generalize that boson table to other Anyon models. I don't know how to do that. But yeah, sorry for overrunning. Yeah, thanks for your time. Thanks for listening.
So if I understand correctly, the color code is 2 copies of Torah code. Mm-hmm. So what happens is that in the two copies of Torah code are different bosons. You condense them mm-hmm. and give you different Torah code. So if that's the case, then in your construction, there should be a step which is gauging, because you implement the symmetry of a Torah code to Torah code. Mm-hmm. And what you describe is 2 condensation, not the inverse. So where is the gauging in your construction?
I don't know if I know what gauging means very well. Okay, here's the thing. Let me try to say one more. I put in a couple of bonus slides. So here's the thing with the unfolding. There are lots of different ways you can unfold the color code into. There are 72 different ways you can unfold the color code into 2 copies of the toric code. I've got some pictures here where this is how I say a E is a red X, an M is a blue Z, and then on the other layer it's a blue X and a red Z, make the E and the M. And well, the condensate in this picture is here I condensed a region of the color code and I made a puncture in one copy, not the other copy. Okay, but that's only if I condense one of these 4. The nice thing with the boson table that goes a bit beyond the unfolding picture is you can very easily describe how to condense all of these other ones that lead to something, let me call it gauging without knowing what that means, but this boson table is maybe hiding what you're asking for.
I have one question. So in the Ha-Hastings code, you have to be careful with the schedule when you introduce boundaries, because you can measure a representation of the logical operator at the boundary. So you need to modify the schedule. Mm-hmm. So it seems your way of thinking about it automatically takes care of this. So could you say a bit more about that?
I think, well, I mean, we built a lot of it. I mean, we tried a few things and not too many things really went wrong. We had this intuition using condensation that this is how a boundary transformation had to work. And we did it microscopically and it worked. Yeah, I don't have much more to add than that.
Thanks. If there are no further questions, let's thank Ben again.